Today's colloquial speaker is Rouven Essig. Rouven was born and grew up in South Africa, was an undergraduate in Johannesburg, then went to graduate school nearby there at Rutgers. After graduate school, he was a postdoc at SLAC for 2 or 3 years, for 3 years. And since around 2010, 2011, since 2011, he's been on the faculty of the Stony Brook University. He works, he's a particle theorist, a phenomenologist. He works in the 3 frontiers of particle physics: the intensity frontier, the energy frontier, and the most exciting frontier, the cosmic frontier. And for the past couple of years, he's been very involved with theories of dark matter. And he works very closely with experimentalists, and he's welcome in experimental collaborations because of his clear vision, and he can actually speak to experimentalists. He uses, not small words, but he can speak to experimentalists. The title of his talk today is Direct Detection of Sub-GeV Dark Matter, a New Frontier. Rouven.
Thank you. Thank you very much for the invitation, and also.
I didn't drink enough.
Come on. Okay, thanks very much. It's really great to be here. So this is my first visit to the University of Chicago. So it's great to finally be here. I've had a lot of very nice discussions with several of you. So I'm going to talk about direct detection of low-mass dark matter. That's the topic that I've been thinking about a lot over the last few years, and I'm very excited about it. I want to share some of that exciting things that have been happening. Now to begin, so I want to start with a big picture introduction. This is a colloquium after all. So I think this audience is sufficiently indoctrinated, not sufficiently exposed by dark matter. I don't need to spend much time on this. So there's a lot of evidence that dark matter makes up about 85% of the universe's matter. I'm going to flash some iconic pictures which show evidence for dark matter. And there's a lot of evidence that these data are described by a new particle as opposed to some modified Newtonian mass or something. So the question really that I'm interested in as a particle physicist is, what is the dark matter? So all the evidence that we have for it comes from experimentation interactions. And in particle physics today, one of the most important goals is to uncover its identity. And what we mean with that, we want to know what is its mass, what is its spin, how does it interact with standard model particles, does it interact with other particles? Is it part of a hidden sector which has its own forces and a more complicated sector with other particles in it? We want to know the answers to these questions. Now, one of the favorite candidates for many decades, and still a very important dark matter candidate, is a WIMP, a weakly interacting massive particle. And what I mean with weakly interacting massive particle is something that interacts with the standard model weak force, so with double Wilson photon. And I've shown here a mass scale, because I'll get back to that in a second, this mass scale. But here is GeV, TeV, so all energies are measured in terms of natural units, so C is 1. So this is the proton mass roughly, here's the top mass, the heaviest standard model particle we had, and half an energy, that's the electron, just as a reference. And WIMPs are roughly between a few GeV and 10 to 100 TeV. And they're basically confined between this mass range in order to get the right radical abundance, otherwise we'll have too many of them. And WIMPs are motivated by several favorite considerations. So a weak interacting massive particle, so a particle that has this mass and interacts with the standard model weak force. If you imagine that that's gets created in the universe, you can get the correct radical abundance approximately. And in addition, we think there should be new physics at the weak scale anyway because of something called the Higgs hierarchy problem. And those kind of theories, like supersymmetry, have with them particles that could be the dark matter. So there are a lot of interesting reasons why WIMPs are, favorite candidates. And right now, the experimental searches for WIMPs are very mature, and we've got very big experiments, very big, expensive experiments that are going on for WIMPs, and so far we've had no success. So WIMPs are still great, but I think over the past decade, the frame of efforts have shifted to consider also other dark matter candidates that span a vast mass range. And I think the shift has happened for several reasons. So first of all, the obvious one is that we have not seen WIMPs. Okay? The other reason is that so far, at least, LHC has not found new physics at the weak scale that might give rise to something that accompanies the WIMP. And also theorists have realized that there's many different ways to get the correct radical balance, how to produce dark matter in the universe, how to get what the gravity bounce is today. So theories have considered a much larger mass range instead of this. We're now considering a large range like this, where you get at the bottom roughly 10 to minus 21 eV, 10 to minus 22 eV, and all the way up to Planck mass for a fundamental particle. And WIMPs lie in this little mass range here. Now, just generically speaking, we know that the dark matter can't be lighter than this. If it were, then its de Broglie wavelength would be larger than the size of dwarf galaxies, which and so it wouldn't form the dwarf galaxy that we do see. So there's some lower bound. If it's a fermion, actually there's stronger constraints because you also want to form dwarf galaxies, and because of the Pauli exclusion principle, you can't stuff enough fermions into a dwarf galaxy if its mass is lower than a keV. So there's a rough lower bound of around keV for fermions. And there's many candidates that people have, of course, considered previously, for a long time already, like the QCD axion, which spans roughly this mass range here. There's something called warm dark matter, like stone neutrino. And at the bottom end, there's recent renewed interest on fuzzy dark matter, but that's also actually an old idea. So one could actually even go higher in mass and think about massive composite dark matter or primordial black holes that have much higher masses. So you would have considered also masses to the right of this. But yeah, we're going to confine ourselves to here for now. So at the bottom, when the dark matter is a boson, below keV, between Z and keV, I'll call this ultralight dark matter. And here the dark matter is a boson, so some scalar particle or a pseudoscalar, like an axion, or some vector particle. Okay. And then above here, we can consider, very generically speaking, dark matter that is part of a hidden sector. Okay. So theories are beyond, so not WIMP dark matter, but dark matter that has maybe some new interactions. Very generically, they will come in some hidden sector. So the idea is that there's a hidden sector which could contain several particles, potentially including the dark matter. It can contain its own forces in this hidden sector. And then there's a standard model sector with all the forces that it has, and all the particles that we know. And there could be some media between these two sectors. But it doesn't have to be. So clearly, if you look at this, there's a rich number of possibilities. Okay? But on the other hand, this mass plot is a little bit misleading, because once I actually postulated a particular dark matter candidate that has interacting with standard model particles, the constraints are often very strong in particular masses. So you can get constraints from cosmology to astrophysics. So it's not that anything goes. So once you actually postulate a particular thing, you have to be a little bit careful about what the constraints already are. The other thing that's important to know, just in very general terms, we have to actually, in order to say what to look for the dark matter, in order to search for it in the laboratory, we need to actually postulate a particular type of model, particular type of interaction that this dark matter might have, its mass that it might have, its spin, and so on. So we need to postulate a particular candidate to actually know how we can search for it. And even though there's so much possibilities, we can write up particular model scenarios, particular models, where there are very sharp and testable predictions for cosmological, astrophysical, or terrestrial observations. Okay. But clearly, what we need is a broad search program in order to cover the dark matter across a vast mass range and not just focus on a few masses. So, over the last few years, or the last decades, I should say, there's many experiments have been done, and also there are many experiments right now that cover a pretty small mass range, so looking for WIMPs, which is a good thing, right? There's great candidates. Many experiments, Large Hadron Collider, the various direct detection experiments, and also the Gamma Space Telescope. And at the low mass range, there have been some experiments, but there's maybe like one biggish experiment that, if you like, that the DOE right now is funding, ADMX. And clearly, though, there's still a vast mass range that remains unexplored. Now, what's interesting is that over the last few years, there have been many ideas that people have come up with, and new experiments that have started to be developed in order to explore much of this parameter space. And that's actually very exciting, that there are ways to explore particular dark matter candidates across this whole mass range. And if I had to summarize some of my research over the last few years on a slide, very roughly sort of in a global picture, I can start with this kind of picture here, where we've got this hidden sector of dark matter, there could potentially be meteors with standard model particles. And the one question I've been asking is, where are the holes where are the particular gaps in this parameter space that experimental not covered? And I'll talk about one today, where the dark matter where you might be able to see the dark matter in terrestrial experiments by having a scatter of some particular standard model particles. Another, I think, interesting question that sort of people have thought about in the past, and we've been thinking about this as well, is very generically, if you imagine that the hidden sector has a dark matter in it and has its own forces, these forces allow the dark matter potentially to have self-interactions. The dark matter can self-scatter, as in here. Or what you can also get is dissipation of the dark matter. So the dark matter can self-scatter and emit a light mediator, some light particle like a dark photon, and that allows the dark matter to lose energy. And with that, for example, you can form exotic compact objects that you could look for at fantastic observatories today, like Gaia, and upcoming ones like SST, or also they could merge and look for them in LIGO. So there's a lot of work, I think, to be done to explore interesting hidden sector dark matter models where they might give you interesting signatures for gravitational observables, even if there's no connection to the standard model at all. And then finally, I just want to mention this, I'll say these in a second. So we can also look for the media directly, and there's an experiment that my collaborators and I proposed about 10 years ago, and that's called APEX, and it's looking for a dark photon mediator. And that experiment is taking data as we speak. Okay, so I'm not going to talk more about this, but I just want to mention this. Some of you will have heard about APEX before, those of you who are old enough and have been around for a while. So here's a picture that I took a few weeks ago of the APEX at Jefferson Lab, and we hope to cover a little bit more of the dark photon parameter space. Okay, so that's taken data as we speak. Well, actually, that's not completely true. I wrote this slide a few days ago. Right now, the accelerator's down, but anyway, so this is taking data in this month. Okay, but getting back to this, so clearly what we need is a broad search program in order to look for dark matter and to maximize the chances of identifying it. And the Department of Energy has realized this as well, for example. And there was a workshop that was organized, that was requested by the Department of Energy called the Basic Research Needs Workshop. In this case, it was focused on dark matter, small projects. The idea wanted to know what other small projects, small experiments can be done to look for dark matter in this vast mass range. Where else is it interesting to look for dark matter? And Rocky was the co-chair of this workshop. And the DE report that was written argues for a comprehensive experimental program in 3 different directions: to direct detection, coherent field searches, so by that I mean low mass ultralight dark matter searches, where the dark matter behaves like a wave, because it has a lot of wavelength. So it looks like things like AEMX, for example, and then accelerator-based experiments. Unfortunately for me, Gordon probably gave a very nice talk 2 weeks ago, talked about accelerators. Okay, so I have to cover that. And what I'll focus on today is direct detection experiments. And I was one of the panel leads with Dan McKinsey and Catherine Zurich. And I'll tell you a little bit about what's been going on in the field of low mass direct detection. So that's going to be the focus of the main talk. So let's focus on the mass trains that I want to consider. Okay, so here I've drawn it from a KV to TV. Here are my whips, about there. And again, down here, there's hidden sector dark matter, so dark matter with some new mediators. And the idea would be the dark matter can scatter all my standard model particles in my detector, and I can try and look for signals from something. And I'll tell you what the something can be. And since we can have different mediators, we want to probe both potential interactions with as many particles as we can, so nuclear interactions as well as electron interactions. And that's going to be the focus of this talk. And I'll just say, so I'm going to focus more on the MeV to GeV range. I colored this actually slightly different color. It actually turns out that it's harder to come up with viable models that can be detected in the laboratory if you go close to the KV scale. So there's very strong astrophysical and cosmological constraints down here. But I think this is a big gap in the experimental searches at the moment, which many people have been starting to fill, trying to come up with ideas to try and probe this in the laboratory. And I'll just mention, I want to talk more about this today, just to keep it simple a little bit. You can actually, for the same kind of experiments that I'm going to talk about here, they can also probe ultralight dark matter, in which case the dark matter doesn't scatter off standard model particles, but the dark matter is actually absorbed by standard model particles. And the same experiments that you would look for here, where you have some recoiling standard model particle, for example, you can also absorb the whole mass energy of the dark matter and look for some recoiling standard model particle, and that allows you to go down with the same techniques as here, allows you to go down to much, much lower energies. to mention this, although I won't discuss it more. Okay, so the outline of the rest of the talk after this introduction is going to be, I'm going to talk about direct detection, give an introduction to this, just the basics. Why is it difficult to do the ordinary thing that you do for WIM searches? Why is it difficult to do that for low mass dark matter? I want to discuss that. Then I'll give you two detection concepts in low mass dark matter. And I'll talk about the Sensei experiment, which is the first dedicated experiment to probe dark matter with masses in roughly this mass range. Okay. So let's start with the basics. So maybe this is sort of as a big picture introduction again to this idea. So our solar system is inside a large dark matter halo. Now we don't exactly know where all the dark matter is. We can simulate it. So here's a simulated picture. This is actually a pretty old simulation of a dark matter halo. So everything that's bright here is dark matter. This is, yeah, as I said, a pretty old simulation. And we can ask the question, where does the Milky Way sit inside this dark matter halo? So here's a artist's conception, clearly, of the Milky Way halo. This says 2005. I'm not sure how it changed since then, to be honest. But here we are. So here's the 2/3 out of the distance from towards the galactic center. So about 30,000 light years. Here, roughly, is the Earth. And if we can ask the question, how large is the solar system compared to the Milky Way to the dark matter halo, is roughly this scale. So we are sitting inside a huge dark matter halo. And if we ask the question, how much dark matter is near us, we have about, so what we do know is that the dark matter density near the sun in our solar system is about 0.4 GeV per cubic centimeter. So if we imagine a wind particle, like a typical wind particle, 100 GeV, your weak scale particle around the Higgs mass or the WZ boson mass, then in a quart of space, so here I drew a little milk carton, so in that size space, we have about 4 wind particles at any given second. If we go to lower masses, we actually have more particles because we have to make up the energy density. And there we have about 400,000 particles. So going to lower mass actually helps us because we have more particles, dark matter particles we can interact with. And the typical speed of these particles is a few hundred kilometers per second. So now what we're going to do, we want to try and detect these dark matter particles in the laboratory. So we put a detector, one traditional detection concept that people have done for direct detection for several decades now. Is that you take a detector with lots of atoms and you put it deep underground. You put it deep underground to avoid cosmic ray backgrounds, which can interfere and limit the signal. And then you wait and you wait and you hope that the dark matter particle that's in the halo will interact with my nucleus in the detector, scatter it, and that nucleus gets a kick, and there's some energy that that recording nucleus gives you, some signal. And that signal is going to be heat, light, or charge, typically. And then you measure the heat, light, and charge, and if you can say that there's no way that a standard model, that some background processes could have caused this, then I can claim this discovery dark matter. So people in this business, there have been some claims of discovery. None of them have turned out to be convincing. So people have been good at making extrusion plots, and a typical extrusion plot looks like this. So here on the y-axis is the cross-section, so the interaction strength of the dark matter scale of nucleons, so nuclei, as a function of the dark matter mass. Healthy, this plot is labeled WIMP, so this is the WIMP. That's what people usually look for. So GeV, 100 GeV, and 10 TeV. And it has a typical shape like this, so everything gray is excluded. At the bottom, the reason why this curve increases like this is because the nuclear recall energy is just too small. So the dark matter mass is so small that it can't give enough of a kick to the nucleus in order to give a signal that you can actually detect. So there's some thresholds to the experiment. And at high masses, the rate it scales linearly with the mass. The rate is proportional to the number density of dark matter particles around us, but that changes the function of the mass. All we've measured is the energy density. So the number density is rho over m, and the rho is fixed. It's 0.4 GeV per cubic centimeter. So as I increase m, the rate decreases, and therefore, if I don't see something, the constraint on how strongly such a particle can interact with the detector decreases. So the direct detection landscape has been very busy, and I'm just showing sort of the latest and greatest constraints on this plot. So here, everything in gray above these lines is constrained, and there have been many different experiments, and at high masses, above a GeV, the leading experiments are Lux and Xenon 110. And this yellow region here, that's when you start being sensitive to solar neutrinos. Okay, so neutrinos coming from the sun and also mimicking the dark matter detector. Then there's lots of projections from experiments that are planned in the future. So these are dash lines, the super CMS, and also the big xenon and argon detectors coming up at higher masses. And they're looking for WIMPs, which is great. This program is very active, as I said, it's very important, and also exciting because we might see something. Okay. Now, why is it difficult to probe low mass dark matter with these, with the traditional way of looking for it? We're looking for elastic nuclear recoils. So the reason is that the recoil energy of the nucleus drops very quickly as the dark matter mass is lower. So here's a plot of the maximum recoil energy that I can get from a nuclear recoil. Is the microphone down? It died?
Just that.
Or just died, so do you want to fix it, or if I speak loud enough, is that okay?
Oh, you're right.
Maybe the batteries are already drained, even though they're new. I don't know if the batteries are
The
still working.
microphone died.
Use that, okay. Okay. So on the y-axis is the maximum nuclear recoil energy that I can get for a dark matter particle skeleton nucleus. And on the x-axis is the dark matter mass in MeV. So here's 1 MeV, here's 1 GeV, and here's 1 EV of recoil energy. And the energy of the recoiling nucleus is the momentum transfer squared over twice the mass of the nucleus. And the maximum value that the momentum transfer can take on is 2 times the reduced mass of the dark matter in the nucleus and times the velocity of the dark matter. And if I put in the numbers, then basically for low mass dark matter, the reduced mass is just the dark matter mass, and I get this equation here. And what you see is that this scales as the dark matter mass squared. So as I lower the dark matter mass, the nuclear recoil energy drops quickly as a square of the dark matter mass. And that's what explains these shapes of the curves, they drop very quickly. So for example, a 50 MeV dark matter particle produces only about a 1 EV nuclear recoil. And it's very difficult to detect that. And the best detectors today, as far as I understand, with TDS detectors, they can look for heat from such a nuclear recoil, may just be able to see some signal like this. Okay, they're getting there. But if you actually ask the question, how much kinetic energy does the dark matter actually have? That, of course, just drops as the mass of the dark matter. Okay, so that just drops as the mass of the dark matter, so it decreases linearly, of course. That's just kinetic energy. And what you see is that there's actually low masses, there's a lot of kinetic energy that's available that the dark matter has, which is lost if we just look for elastic nuclear recoils. So a more promising approach, rather than looking for elastic nuclear recoils, is to look for inelastic processes of some form. Okay? And I'll give you 2 examples today that I'll focus on. So this often allows, by looking for inelastic processes, then energy momentum conservation allows you actually to transfer an order 1 amount of the kinetic energy of the dark matter, in particular its atoms. And in that case, instead of a 50 MeV dark matter particle producing 1 EV, a 5 MeV dark matter particle is going to produce 10 EV of energy. And a 1 EV particle, a 500 keV dark matter particle will produce 1 EV. So that, in principle, allows me to go down towards the magnitude of mass if I somehow can look for entire dark matter kinetic energy. If I can look for a process that allows me to do that. Okay. So there's been many ideas for how to do this, okay? And there's been a recent explosion of nuclear architecture ideas. And this is a plot that I made for this basic research needs workshop with input from many different people. Here's the dark matter scattering cross-section of nuclei as a function of the dark matter mass and MeV. So here's 1 MeV. Here's a GeV. Okay, so we're just focusing below that. Here's the current existing dilatation constraints. They go down to a few hundred MeV. And you see this vast open parameter space that we potentially probe with new ideas and new experiments. And of course, the further you go to the left, the more challenging things become because we're looking for smaller and smaller signals. But that's the goal, to go as low as we can. Here's another plot for electron couplings, so dark matter scattering electrons for different type of models. So here are the existing direct detection constraints that go basically down to MeV or so, and I'll allude to those a bit later in this talk. And again, there's lots of ideas to cover lots of open kernel space. And in this talk now, what I want to do is I want to focus on detection concepts that have been developed by myself and collaborators, and also, so these that can be currently realized now, or can be realized in the near term. And basically what I want to focus on the left side, is an idea using molecules, which is still an idea, it still requires R&D, but that sort of fills in a nice little gap that exists in the near term of probing down to 500 keV up to 10 keV dark matter. So, and on the right side, I'm going to focus on ideas above an MeV. But there have been ideas also to go lower, and one of the experts also here, but Johnny spoke a lot about this. So you can tell you more about some of these ideas which he's been involved in. Okay, so now let me tell you about detection concepts for low mass dark matter. And I'll mention two ideas. One of them still requiring some certainly R&D efforts, but this will be very brief about molecular excitations to probe nuclear couplings, and then another idea is to look for electron recoils. So let's start with the molecular excitation idea. So this is work that's in progress. Hopefully we'll have a paper soon within the next few weeks with my study group colleague, who's a quantum information science person, Eden Figueroa, and then three great postdocs, one AMO theorist, Jesus Perez-Rios in Germany, and then two particle theorists, Harikrishna Ramani at Berkeley and Lawrence Stone at Princeton. And here the idea is the following. So let's consider a molecule like carbon monoxide. So this is my representation of carbon monoxide. The dark matter comes in and hits this molecule, and it's going to shake it, it's going to excite a vibrational mode in this molecule. What this does, so I've got here's some schematic potential. So instead of these label different vibrational modes. It's in the ground state initially, so you cool the gas enough to be in the ground state. The idea is that you excite to some higher vibrational mode. And this, because it's an inelastic process, actually allows you to transfer an order one amount of kinetic energy. And you can excite a vibrational mode, so the lowest lying mode in carbon monoxide is about 250 millieV. And you can imagine exciting, though, a higher vibrational mode up to 7 eV, roughly 5 or so. Then the idea is that this excited vibrational mode will de-excite step by step, and in each step we'll get a photon. And there's different ways that the photon can be created, but let me just give you this simple picture. And what you get is that the molecule relaxes back to the ground state, and there's several photons that are of energy between 100 and 250 millieV. Because as you get higher up, these spaces become actually narrower. So very high up, these step-by-step de-excitation will give you photons that are lower than 250, but somewhere in this range here. So the concept, at least on paper, very simple. So here's what we have is a tank consisting of a gas and molecules. At some temperature, we chose about 55 Kelvin, and some pressure, 5 millibar. And then the idea is that you have photodetectors that instrument that tank, and you look for the photons coming out. The nice thing is that you get multiple photons, so you don't have to worry about the photodetectors producing fake dark counts, so fake signals. Clearly, there's more work needed on developing photodetectors, but there's actually several promising avenues to look for this. So one can use superconducting nanowire single photon detectors, or transition net sensors, which at the moment are not that far off to actually try and measuring these things, or even microwave kinetic inductance detectors. And we've been in discussions with several experimentalists to try and realize this in a laboratory where one could imagine having a prototype experiment in the next 2 years. So what would that give you? So it would allow you to probe spin-independent scattering, so nuclear couplings, dark matter nuclear interactions, I should say, down to a few hundred keV. So never mind these names exactly, but there's different ways that the photon can get generated. So here's a little prototype experiment that seems feasible on a 2-year timescale. And then one can imagine a bigger one, of course, that would get you a bit lower. And also, you can also, by taking carbon monoxide, by taking different isotopes of carbon monoxide, we have an odd number of neutrons. You can also imagine probing spin-dependent interactions. And you can probe spin-dependent interactions well below a GeV scale. And that's the only concept that I know about. We can actually go well below GeV with neutron spin-dependent interactions. Sam?
Just to get a sense of scale for the pressure that you mentioned and this mass, how big
So the prototype is about a 20 centimeter cube detector. The other one that's a bit larger is about a 2 meter cube. So 2 cubes, so 8. Okay. Yeah.
So to contrast this with like the Stanford group's proposal for absorption of bosonic dark matter molecules, so was theirs looking for electronic excitations as well as vibrational modes? And also, how is their readout different from yours?
So they have one photon they're looking for, so you really worry about dark counts, so you have to just control those. And the energy, though, depends exactly what molecular, what vibrational mode you want to excite. So they could be, and what the mass of the dark matter is, because you absorb the whole energy of the mass. So there's different things that they consider. But in spirit, it's similar, but the signal is very different.
So is the problem is you can't randomly absorb to this higher state and then cascade down?
For the scattering.
For the absorption.
Absorption, it is a resonance enhancement. So if you're sitting, if the mass is right, has the right energy, then there's some enhancement, which we don't have. Right, so their projections look more spiky than ours.
So why do you choose gas as the target? Why don't we use solid?
So we want to have vibrational modes that relax via decaying by emitting a photon. And if you make the pressure too large, there's other ways that it can be excited. Yeah. But I've actually had some very interesting discussions with Carlos, one of the students here, and he was thinking that maybe we can actually use like liquid or so. So anyway, so I think if you have some ideas or so, we can have to discuss. Okay, that was very quick, but that's all I want to say about this. And now I want to talk about electron recoils. Okay. So the idea is very simple in principle. In practice, it gets hard, both from the theory point of view and also from the experimental point of view. So the idea is that you can use dark and electron scattering to probe well below the GeV scale. And if you imagine again, my little atom, now we're going to focus on the electron. The idea is simple, you're going to scatter the electron, and this type of signal, that you might get, is you're going to produce one to a few electrons. Okay, it depends a little on the detector setup of what exactly you're going to get out. But imagine that you're going to be looking for one electron. If you just hit the electron and it goes on its way. But you can also imagine that if this has enough recoil energy, that this electron could ionize other atoms or produce more electrons in some way, and then you can also look for a few electrons. And I'll explain this a bit more as we go along. But because it's an inelastic process, this actually also allows you to transfer an order 1 amount of dark matter kinetic energy to the electron. So this also allows you to probe any dark matter if you had a system which has an electron volt excitation energy. So there's many different types of targets you might want to consider for dark and scattering electrons. And we just run through a few of them. So one obvious one, because there are very big experiments that look for nova liquids, and that have nova liquids. So like a xenon detector or argon detector. So if you imagine that you've got some xenon atom, so you can ask the question, what's the excitation energy, the binding energy of the outermost electron? It's going to be order 10 electron volt. Okay, so hydrogen has 13.6 electron volt. Any massive nucleus or any large atom, the outermost electron will have roughly order 10 eV binding energy. So very roughly, that's what you need to, that's the energy transfer that you need to have to the electron from the dark matter. And that very roughly gives a mass threshold of about 5 MeV, if you can see the recoil of the electron.
This is the dark matter scattering.
Dark matter scattering of the electron. Not absorbing, scattering. Okay. Another thing you might imagine is to use a semiconductor. So to remind you of some basic semiconductor physics, so a semiconductor is basically, here's the energy level diagram for a semiconductor. So the y-axis is energy. You have a filled valence band that's filled with electrons. The idea is that the dark matter comes in, hits one of these electrons in the valence band, and excites it to a conduction band where it can move around. And there's a little gap between these two things, which is called the band gap. And that band gap in different semiconductors is of course different, but it's going to be of order 1 electron volt. Okay, so in silicon it's 1.1, in germanium it's 0.67 electron volt. And in principle, if you can do this excitation, so dark matter comes in, hits an electron, excites the conduction band. If you can see this electron, you can probe down to 500 keV dark matter masses. Other targets that people have considered are very similar to this, like scintillators, where you hit the electron, the valence band, it gets excited in the conduction band, but instead of trying to manipulate the electron and seeing the electron, it could recombine with the hole that was left behind and emit a photon. So you can look for scintillation light coming from dark matter and scattering. And that very roughly has the same kind of mass range. And there's many other ideas that people have considered, including Tommy Donald here, where people look at graphene targets, superconductors, Dirac materials, photocrystals, where the gaps can be as small as a mini-eV, which in principle allows you to probe down to keV masses, if you can see the signal. So what's the status of these different things? So the idea of Toulouse Nova liquids, this is actually several years old, and a few years ago we managed to put the first constraints down to 5 MeV dark matter by looking at old Xenon 10 data that was taken around 2006, 2007. And then with Xenon 100 data that was could be done as well. And also Darkside 50 using argon, they released the result from dark matter scattering a year ago. And there's a new proposal called Albeca. So the problem with all these previous Xenon experiments, and also the existing ones like Xenon 1 ton, or Lux, etc., is that they see a lot of single electrons. There's a huge background. And there's some ideas of where these backgrounds are coming from. But the idea is to really control these backgrounds, which you want to do extensive darkness search. That is a challenging thing to do. And Albeca is a little collaboration that exists. So Albeca stands for Low Background Electron Counting Apparatus. The idea is to put a 10 kilogram xenon detector on the ground, where the focus is really on reducing these electron backgrounds. And this is a collaboration between Adam Bernstein, Raphael Lang, Kai Chwani, Peter Sorensen, Jing Zhu, and then there's 3 Stony Brook people, myself, condensed matter theorist Marie Fernandez-Serra, and a student of ours in condensed matter who's involved. And the reason a theorist like myself is involved is because there's actually a lot of work still needs to get done to properly calculate the dark matter electron scattering signal in a liquid xenon target. It's not trivial to do that because the electron is part of the sort of main body type of system. Okay. But I want to talk about that more today. Now, for semiconductors, that's going to be a bit of the focus. So there's been first success by Sensei and the CMS collaboration in probing down to 500 kV masses using silicon target. And there's 2 funded experiments, Sensei and also Dynamic M, who of course there's a lot of big effort here on Dynamic M. And I'll tell you about Sensei in particular very soon, but a lot of the stuff I'll say will also be applicable to Dynamic M. And then for gallium arsenide, there's actually very nice R&D going on from our collaborator, Steve Lorenzo at LVL, where he's been optimizing the gallium arsenide as a target, and there's also work that needs to be done on photodetectors. But that seems like something that can also be done over the next year or 2. And then there's, for many other ideas down there, there's partially some R&D ongoing, so Yannick, I'm sure, can tell you much more about this, or R&D that's required to realize this potentially great thing that we can go down to kV masses. And the thing that's very exciting, I think, is that there's lots of exciting collaboration between particle and condensed matter theorists to try and understand these various exotic materials and also to calculate these rates properly, because it's not always that trivial. And of course, we need to talk about experimentalists and instrumentalists, because they're the ones that actually have the cool toys that make this possible. So now, let me tell you about the Sensei experiment. Okay. So Sensei stands for Sub-Electron Noise Skipper CCD Experimental Instrument, and that name will become clearer as we go forward. So we are a small collaboration, about 20 people, 4 institutions, Fermilab, Stony Brook, Tel Aviv, and Oregon. And it's fully funded by a private grant, by grant from a private foundation, from the Heisen Science Foundation, and as well as Fermilab. And at Stony Brook, for example, we have 4 students that are involved, 3 experimentalists and 1 other theorist who've been helping with the data analysis. And we exist, there's a bit of a picture. Yeah. So what is Sensei's target material? So the Sensei's target material are special silicon CCDs. Okay? So let's start off with saying what is a CCD. So a CCD is a charge-coupled device, and the idea basically of a CCD is that light incident on a CCD will get converted to electrons. And then you read out that signal, the electrons, and you reconstruct the image. And you get beautiful images like this. Okay? We don't want to see this, although that's cool. We want to see dark matter somehow, okay, in the following way. So Sensei's target material are special silicon CCDs. They're called skipper CCDs. So here's a picture. This picture has, so this CCD has about 1 million pixels on it. And the detection idea is that dark matter would come in, so here's my CCD with a lot of pixels. If I zoom in on one particular pixel, then in that particular pixel, I've got my silicon. And if I look at the energy level diagram of the silicon, I've got dark matter coming in, hitting my electron, exciting the conduction band, creating a few electrons. So I can create one electron, or I can also create a few electrons if this electron gets kicked up high enough in the conduction band, and then relaxes back to the bottom of the conduction band and create additional electrons as it does that. Okay, so that's possible. So the event rate for this happening, of course, depends on the interaction strength. And so here's a plot of the spectrum of what we might get for a dark matter particle that scatters off an electron in the silicon. So here on the y-axis, I've got the dark matter recoil spectrum, on the recoil number of events. On the x-axis, the number of electrons I will create in a typical process. I've chosen a particular dark matter model here and a particular mass of 10 MeV. It turns out that this cross-section, at this cross-section of this particular model, I can actually get the correct value of in some particular way, which I'm not going to discuss, but this is actually a realistic model, realistic number of events that we'll see. And you see that the rate, so here's the number of events that I get that produce one electron, so about 2,000. Here, about several hundred, I produce 2 electron events, and you see the sharp drop in how many electrons I produce. So there's a sharp drop. Yeah.
This is a very young question, but why is the background flat?
Oh, the background, so I didn't put one. So the background, in this particular case, comes from Compton scattering. So I've got photons that are created in the surrounding material, with radioactive decay, etc. They produce some photons, they scatter an electron. The photons will typically have very high energy, like keV, tens of keV, etc. But there's a little tail, which is pretty flat, that goes down all to the lowest energies. But because I care about a very small energy range, it's small, okay, and it just turns out to be flat. Okay. Okay. So, oh, sorry.
So can you think of that as basically, it's like a kind of like glancing collisions of a high energy photon off an electron,
Right.
The phase space is very small.
Yeah. Okay. So, before June 2017, the best detectors that existed, which actually were from Damic, the old Damic, or the existing Damic actually still, before the new super CCDs, so these are using all CCDs. They were sensitive to electrons with events with 10 electrons or more. Okay? So if you were looking for dark matter electron scattering, they would be missing out on this huge signal rate at lower electron number. But with the skipper CCD, we're sensitive even to single electrons, so we actually see this huge rate potentially. And of course, I should say that, so Noah is here, you can talk much more about him. CDMS had some great success using a totally different technology to see the same thing. So they're also sensitive to single electron events. I'm happy to talk about this more afterwards. Here I'll focus on sensing. So here's how a CCD works, very roughly. Okay, so I've got a picture here of a cutout of a CCD, where each of these is a pixel. At one of the corners, there's a readout. Okay, so that's where I'm going to measure my charge. And let's now say I've got some sprinkling of electrons that I expose. So I expose the CCD for a bit, and I get some sprinkling of electrons across the image. So here's 3 electrons, here's 2, and here's 2, and everything else is empty in this example. The way I read is I shift everything down by 1, pull the charge down, and then what I do is I start reading in this particular schematic here from left to right, and I measure the charge that's in here. And I shift things over, and each time there's a new shift, I measure the charge. And the way the charge is measured is that you can think of this reader here as basically a little capacitor. If I move some charge in it, it changes the voltage. What I'm actually measuring is the voltage. So I measure roughly 0, etc., and then I measure my 2 electrons, etc. And then I repeat everything where I shift everything down again, and I read again. And I just keep doing this, and this is how I read out my image. Now, ordinary, we call it scientific CCDs, the best readout noise, RMS readout noise that has been achieved is roughly 2 electrons. which means that if I make a reading here, the error that I get on that measuring number of electrons in that particular pixel is about 2 electrons, which isn't bad, except that I've got a million pixels, and I make this measurement a million times. The chance that I get that I measure 10 electrons sometimes, even though I have 0, and it is not 0. The chance that I measure minus 5 electrons, even though I have 1 electron, is not 0. Okay? So that's why you're sort of forced to have a high threshold if you're trying to do a dark matter search. Okay? About 5 sigma by that, so about 10 electrons. Okay? Now the skipper CCD, what that allows you to do is it allows you to sample the same pixel, the charge in the same pixel, multiple times without corrupting the charge packet. So I can make a measurement many times on the same pixel to try and measure the charge packet. Okay. And then what I do is I just take the average of all my measurements. And in the end, that average will have be a good measurement of the real number. So this was developed in collaboration between Fermilab and LBNL Microsystems Lab. And Avi Tuttenberg was the PI of a LGRD, a Lab Directed Research and Development project at Fermilab several years ago, and this was successfully demonstrated. And the achieved RMS noise was about 0.06 electrons. So now you can suddenly do an amazing search for dark matter because you're sensitive even to single electrons, but the noise is irrelevant. So this kind of technology, and also what CMS achieved with their technology, is a big game changer in terms of looking for long-mass dark matter. Dark matter does not want to give you many electrons, so having increasing the sensitivity between sort of 10 electrons down to a few, or 1, is a big change in terms of the sensitivity. Now schematically, how the skipper CCD works, in my theorist way of showing it, or understanding it, is that if I move the chart around, so let's see as an example with 6 electrons, okay? So the idea is that all that you've done is you've changed the readout of the CCD. You've not done anything else to the rest of the CCD. And what you do is that you just make a measurement you move it over, there's a capacitor, you measure the voltage change, okay? And then instead of discarding the electrons and then reading the next one, you just move this back, and you just repeat this however many times you want. And you take the average of those measurements. So you can now count individual electrons with essentially 0 noise. Okay? So here's a picture, a small cutout of an image of a CCD, where you read in standard CCD mode, so each pixel gets read once. So this scale in here, the legend tells you what the measured charge is in each pixel. So between -5 for the blue, dark blue, and 5 for the purple. And you see that this is all over the place. And if I were to tell you that there's 1 electron sitting here, you wouldn't know. Okay? But here, I'm measuring with the skipper CCD each charge multiple times. I know that all these pixels are actually empty. There are no electrons in them. And here's an event with 1 electron. And instead of looking at something like this on the left, where this is the number of events as a function of the electron number of electrons that are being measured in the standard CCD, I can now distinguish pixels with 0 electrons, 1, 2, 3, 4, etc., and even going up to 1,000. Okay, 1,000, 1,001, etc. And now you can understand what sensor stands for. So sub-electron noise, because it's the noise is below an electron. Skipper CCD, that's what we're using, experimental instrument. Personally, I think we could have got rid of the word instruments, these are just filler, because I think experiment just makes a lot of sense. Okay, so here, what we have been able to do is we've been able to have a little prototype detector to get the first dark matter results about a year ago by taking the CCD and putting it on the surface and just taking 3 hours of data. So there's this prototype CCD, which was packaged and tested for dark matter search in actually 2017. Today we then analyzed last year. It's a tiny little CCD, 0.094 grams. They're tiny, so here's a picture of the CCD, not a picture, sorry, here's a card. It's a piece of card that's on your CCD, which I cut out. That's the size of the prototype CCD. Okay? The area is less than a dime. It's actually not a good representation because this is way too thick. The real CCD is about 1/7 the thickness of a dime. Okay? It's a tiny little thing, but you can do science with it and probe new parameter space with it. Okay? So here's what we had a year ago. is the existing limits from, I just alluded to this, from Xenon 10, ones we derived several years ago. And here's the sensor data, which now goes down to 500 keV. And what was nice about, so this is a very low exposure, 0.02 gram days. So if you think about the Xenon N-ton or LZ goals of multiple ton years, eventually what the exposure goal is, but this is like nothing, very low. We're the first one between 500 keV and 3 MeV, and Super CDMS also achieved great success very closely after this, where they measured lower, where we measured under 500 keV.
Sorry,
I'll show that later, by the way, yeah.
So once you specify a model that realizes that form factor, wouldn't there be BBA constraints or supernova constraints?
Oh, sure, so a particular model, yeah. So this is just a, the dielectric constraint. So we talk about embedding in a particular model. And so the other thing that was so interesting with this, and we can talk much more about this, but we actually did yesterday a little bit, this particular data was taken on the surface, so you actually sense it as strongly interacting dark matter. So if you take a detector and you put it deep underground, and the dark matter attacks very strongly, it's not going to make it down to your detector, because it's going to scatter in the atmosphere, and then eventually scatter in the Earth's crust, and it'll make it down to your detector on the ground. If you run on the surface, you don't have to worry about the crust, but you just have to worry about the atmosphere. So in principle, just looking at the detection constraints, sensing covers a huge amount of parameter space, a high cross section, compared to Xenon 10, which was run underground. But of course, the exposure was much more, so that went much lower.
So you see strongly interacting dark matter, but you're measuring the cross-section with electrons.
Yes, strong interacting, sorry to be clear, there's many words strong, so not the strong force. So this is just like high interaction.
Large interaction.
Large interaction. Okay, thank you. Yeah, thanks for clarifying that. Okay? And one can ask the question, does it make sense to go even higher cross-section by maybe taking one of these stupidicities and putting them on a balloon or a satellite? And if there's time at the end, I will have a few words to say about that.
Sorry. You think of the last two questions. I mean, so strongly interacting, the whole point about dark matter is it's not it's collisions.
Right, so you can't have 100% of the dark matter be strong interacting without it having shown up somewhere. Or you could have a subatomic component potentially strong interacting, and it could avoid a lot of constraints.
So this dark matter might
So it's actually
shaped like a halo, it might settle into the disk because of the relative mass. It's like other
possibly,
systems.
yeah. There's actually, so I think this is a very interesting topic, where I think a lot more work is needed. And I'll have a few comments at the end if I have time about strong interacting dark matter, where it's not clear, I think, in the literature, whether it's possible to have a model with very large interaction strengths, where the dark would be subatomic component, but it might be possible to have that.
But there's been a great question about plot, because to make a point in the plot, you have to have a model. I mean, those are physical parameters. And as a direct technical
Right.
terms, you have to have a model of the cosmic distribution of the document to make the plot.
Well, this is assuming a standard Maxwell-Boltzmann distribution.
And a dark matter halo.
And dark matter.
Yeah, okay. So which is maybe not right. So it's
Which maybe is not right, but yeah, so yeah.
All right.
Okay, that's the assumption though.
I guess it depends on the cross section, but it's also different whether it's a strong interaction themselves, or whether it's a strong interaction with matter. But here it's more important. The strong interaction, stronger interaction.
Yeah, here exacts a lot with electrons.
Well,
Potential
all the
nuclei.
happening for light, and it's all strong interaction.
Right. But they're not that strong.
Yeah, so in principle, I guess I can go to a different version. This interaction is itself is still something.
Yeah, so I can make the self-interactions not that
Yeah, so-
strong.
so-
But I think you were talking about,
Almost
you're talking about self-interacting with dark matter or just interacting with matter?
With matter.
So matter, yeah,
because that's
which is what we need to get.
Yeah, but with matter, then it has less implication for whether it's, it's like a halo or so.
Well, it's important.
That
It's
is-
right. So it is important in terms of what to assume for the distribution, because maybe the dark matter doesn't have a nice halo distribution, but actually has
That's
synergies.
more sensitive to specific interaction. So,
Could you remind us this density constraint of 0.4 GeV per centimeter cube? How is it obtained? So what is the assumption that goes into that?
So it's actually taken from measurements from data of how, things molecular clouds and things, stars, I guess, as well, move around within the solar neighborhood, within the kilopascals. There's, of course, an error bar. I think, I'm not an expert exactly what the error bar should be. complaint was that the containment are very small. But I think certainly a factor of 2 is very generous. I think it should be much stronger, much tighter element. Okay, so the prototype that I just showed you the results for the surface run, which was just a few hours long, has been taking data underground near the Minos facility at Fermilab. So here's a picture, which all of you know here, since it's so close to it. So here's the high-rise in Fermilab. And underground, about 107 meters underground, the Minos wall, there's a little tent that sits here. So that's a little tunnel, and on the side here, that's a sensor tent. And I'll probably look for this picture, but as a theorist, I don't usually get to wear a hard hat. But here I'm outside the area in front of this tent. And he did let me inside and take a picture. So here's a picture of the detector and the prototype sitting here. Okay. And I should say that just behind us on the left there, Super CDMS actually has a new facility that they're building. Is it Nexus? Is that the right name? Yeah, Nexus. Okay, good. And they're going to do some tests over there. And that's sort of the 2 experiments going on, two document experiments. Okay, so here's the result that we had. So these are new building constraints for the paper that we just had a few weeks ago. The exposure is a whopping 0.246 gram days, much larger than ours of the surface run. And by a little bit, these are the strongest limits between 500 kV and 5 MeV. Here's the CMS high voltage run last year, where they put very nice constraints in dark matter. Here's the surface run, and then again at higher masses, Xenon 10, at the moment, takes over. So the goal is not to do this little prototype detector. The goal is actually to have a much larger detector, where we're going to have much larger skipper CCDs. So we want to build a 100-gram detector that consists of new and bigger skipper CCDs, so they're going to be about this big, and about 50 of them. So putting together, that makes up 100 grams. And we are preparing a sort of a staged approach where 10 grams will first go to Minos, underground in the same place where the other prototypes are operating now, and then at SNORLAB, so it's going to happen later this year. We plan to build up to 100 grams at SNORLAB over the next year, 2020. The improved sensors, not the prototypes, but the proper production run of sensors will arrive in April, so next month at Fermilab. And we can probe any interesting dark matter candidates, which I didn't really talk about today, but I've got some backup slides if anyone's interested. And just to show you what you can do, let me show you one particular model, so I've got various models that I can show you. But here's the dark matter scattering cross-section of electrons, a function of dark matter mass. Here, the existing constraint from Xenon 10. So up here, I didn't draw this in this plot, there's Sensei and Super CMS constraints somewhere up there. But the goal is to go much, much lower in cross-section strength. And for example, a 10-gram detector running for 3 hours can already probe new parameter space and deep Xenon 10. This is for a light mediator. It doesn't have to be massless, but it could be. That's right. So it could be massless, but it doesn't have to be massless. It could be light. Just light as an less than a few kV. That's the typical transfer. Yeah.
What are the background assumptions for these?
So here we're assuming no background and a 2 electron threshold.
Okay. For all 4?
All those. Okay. Okay. So, and then of course, so this is a particularly nice model where you can see that this isn't just an incremental improvement. Basically, with Sensei, you can have a huge improvement in the sensitivity by having a small detector running for a year, so 100-gram detector. Okay. It isn't like, it's not where you just increase the mass by a factor of a few and then you get a sensitivity better by a factor of a few. It's sort of a big difference, which now this technology allows you to get in darkness sensitivity.
So you eventually measure something, probably you have something in mind that you realize all these ideas, right? A model.
Yeah. Yeah, so I'm going to tell you about models.
And how is it already there? Okay.
Yeah, so there's several. Yeah, I'm happy to talk about it in part. Okay. Okay, so to end with 2 more minutes, okay? 2-3 minutes? Oh, okay. So let me get back to this question about strong interacting dark matter. So strong, like large interaction strength, which we already came up with. Thank you, Rocky. Okay, so large interaction strength. So one question, and this is really a question. I think the literature is extremely confusing on this. There were raising questions in the audience which are very good about does it actually have the same halo formation, etc. And those are all great questions. I think the literature is not clear on this. But let's consider mini-charged dark matter. For mini-charged dark matter, so here's the sigma E, so the dark matter scattering cross-section of electrons function of the dark matter mass. Here are the direct protection constraints, so that's combining sensei, CDMS, xenon-10, etc., etc. Okay, in all one block. Here's bounds from BBN and supernova constraints. Actually, this was something that Sam worked on with me and my student, Jacob. And here's bounds from the stack mini-charge experiment that ran in the 1980s. And here are collider bounds at high mini-charges. So I've converted this to the scattering cross-section of electrons. And there's a question, and as I said, I think this is really a question. It's not clear to me what the answer is. Is this region here still allowed at high cross-sections? So at this region, you have such large interaction strength that the atmosphere is going to block the signal coming to sensei, for example, with CDMS. Okay. There are potentially bounds from C and D and effective constraints and just messing up the C and D power spectrum. If you make this you make the dark matter subdominant enough, it seems that you can avoid those. Okay. So this is assuming like 0.1% or so. And then there's questions about the halo, etc., how that behaves. But potentially this region is still open. And if it is open, you could imagine putting a sensei, or sorry, skip a CZD on a balloon or a satellite to try and probe this high cross-section region where you would just avoid seeing a lot of the atmosphere, so here's the reach for the balloon, and putting it on a satellite where you still have to put some packaging around it, 1 millimeter of minor as assumed in this particular case. And you can put the CCD on a CubeSat or on the ISS, or here's the balloon which can fly in various places. Now, I think this is sort of an interesting question, it's sort of fun. There's a lot of constraints clearly, but it's something fun to think about. And if there is an open allowed camera region, and you would put this on the satellite, the kind of signal you could see would actually be pretty cool. Because, let's put it on a satellite. So here's a simulation that was made by Timon, my collaborator. Let's focus on the red line here, in this plot here and here. This is the orbit of the ISS going around the Earth. I'm going to animate this in a second. On this plot, what you see is the velocity distribution of the dark matter arriving at the detector. So it interacts with the detector with the material outside of the shielding. Outside the detector is going to be stopped. It's going to change the velocity distribution. And the y-axis here is the event rate per gram per second. Now, unfortunately, I forgot precisely what the cross-section is for this, but this is actually pretty pessimistic. So here is 0, 2, 4, 6, 8, and you can multiply this by about 1 million to get the event rate that you would get if you put CCD, if you had this cross-section that's just about the boundary. Okay, but as oh, sorry.
So this is the freezing curve.
Yeah.
Okay, so the cross-section.
I didn't know about that, but yeah.
Probe that is much bigger than this, still haven't reached the cross-section.
Right.
So what does this mean? This means that it will produce more.
Oh, so never mind how you would produce it. Okay, so I'm not asking what
There is a model of independent production.
I'm just assuming that I can get some 1% dark matter component somehow. I'm not specifying exactly how.
Okay, but there is a model of independent production. Because in the early symbol.
Yeah, so if you high cross-section, there's some freeze out, but the freeze out line is
freezing type of production. Even freezing type of production.
no, you're in thermal equilibrium. Well,
this is going to be
Yeah, that's just to guide the eye.
that's just a guide. I could have removed this code because I actually don't want to talk. I mean, I can talk about it. That's actually answers Carlos' question because that's a particular model where you get the right value.
You will freeze out by doing something.
Yeah, but I can imagine some other way of producing it. I'm not specifying. I think it's a good question in general, but I'm not. For this particular case, I'm okay.
Yeah, the irreversible production from freeze out at those cross sections is like 10 to the minus a gazillion. Because the cross section is way too small. So like there's always some other mechanism that provides it. It's not freeze in because you're thermalized. So yeah, we'll worry about that later.
Some other way, which is okay. Okay, but anyway, what you could do if you want to fill this hole, just model independently, fill this hole up as much as possible.
Don't you drown in cosmic rays if you're going this way?
Oh, but the event rate is huge.
Yeah.
the event rate of dark matter hitting it is not huge.
So is the background.
But okay, so here's the signal that you would expect. Okay, so multiply this number roughly by 1,000,000. So here's 2, 4, 6, 8. And as the ISS goes around the Earth, if you look into what signals where the dark matter wind is coming from, if you're in front of the Earth, you see a huge rate because there's no shielding from the Earth. If you're behind the Earth, you see a vastly reduced rate, and you get a huge demodulating signal every 90 minutes because that's the orbit time of the ISS. So yes, there's large backgrounds, but they're not that large. Million events a second per gram, and I can imagine doing a ramp up. And you see a huge modulation. Okay. So it's not crazy to try and potentially discover something like this. And then you can also imagine putting it on a balloon where you shoot it up at JPL, for example. This is what was taken in this example. But the modulation is 12 hours, 24 hours just from the Earth's rotation, where you can imagine shooting a balloon this time and then 12 hours later. So it's not as dramatic, but there's a principle of large modulation. Okay, now, there are a lot of caveats. Anyway, but we fortunately don't have time for them. You know.
So I just want to say the white space is not completely open. If you go to the previous page, there's a lot of new neutrino constraints set by us already. Neutrino
Okay, good. Yeah, so we should update that part.
and also, we also have some like ground-based like PDK and LUC, or you can do it in neutrino experiment. They can cover a lot of the space over there
Yeah.
independently.
Yeah, you won't know it's dark better, so I'm going to still say this will be a good thing to do.
Right.
But yeah, if you find it. But anyway, so I think this is a real question. The literature is not keen on this. Sort of as a fun thing, there is actually a way you can actually look for it. Okay. Okay, and then to finish up, so these are projection and absorption. I talked about that, so let me just finish up. So, getting back to the big picture, the goal is to uncover the density of the dark matter. Compared to several years ago, a much wider class of dark matter models are now being considered. And we can already probe dark matter scattering down to 500 keV with direct detection experiments. So both Sensei and SuperCM has demonstrated this. And there's of course xenon experiments that go down to 500 keV. And I'll talk a lot about Sensei, but we have the first results, and we'll probe vast regions of territory that's really open, and probe several interesting models like Friesen and other ways of producing dark matter in the next 1 or 2 years. So thank you. Additional questions from the audience? Yeah, Al?
Technical question. How cold do you get these things and how fast do you do them out?
So the skipper, there's about 100 Kelvin, and the readout is slower because you're reading everything multiple times. 1,000,000 pixels or so, so it depends how many samples you take of each. Roughly an hour, that's a good rough number, but it really depends. So what we've also done is we've just exposed it for a day, and then read it out within an hour, so exposing it for a long time. So there's different choices you can make, different optimizations you can play around with. There's dark counts that the CCD has, so I didn't talk about all of that stuff, but there's dark counts that the CCD has, so leaving it exposed for too long is going to make you worry about that. There's some other interesting effects the CCD has if you read up too quick. So yeah,
Have skipper CCDs been used in other applications?
No, so Javier and Juan and company, so they're going to be used for dark matter by Dan again, by Sensei. There's other applications that Javier and company are looking at, which is coherent neutrino scattering, where you get an enhancement of low momentum transfer. So the skipper CCD allows you to actually probe that. So there's goals to that. And there's other applications, quantum science that people have been thinking about, but I think it's a pretty new technology, and who knows what's going to come out.
Craig?
You went to the white space plot.
Yes.
So, okay, so you say you go above, the atmosphere, but you can't go you can't go above the galaxy, right? So what I'm thinking about is that the column density of matter just in the galaxy is about 10 to 20 folds. So nothing is going to get to us from that upper corner. When you draw a horizontal line there.
Well, that
So
assumes that assumes it gets evacuated, right? So I mean, it could just be around us. That
It's
was
not evacuating. The point is to get down to it. I mean, if the atmosphere
You're saying that
what's in the galaxy.
You're saying that the galaxy, that it wouldn't actually enter the galactic
Yeah,
distance?
the interstellar medium has that much column density. This is another.
Well, stuff will be inside it to begin with. So Rocky actually wrote a nice paper 10
10-ish years ago.
Well, you got many much, that's one of them. Yeah, so that phrasing wasn't appropriate. Anyways, but yes, actually Rocky had this paper several years ago on what region of mini charges actually would be evacuated from the galactic disk. So we've actually been really looking at this, taking account of fusion, etc. It's really an open question. I think your questions are very good. I'm not saying it's open, right, just to be clear. I'm just saying if it is, we could do something cool. And I hope it is, because this is really cool.
So you've effectively eliminated the read noise with like that last pixel. But at what point do you start having to worry about loss or noise as it travels all the way to that last once the charge travels? Is that effective?
So you're talking about the skipper CCD, the readout? It really is set by the readout state, right? There's no noise elsewhere. Sorry, maybe it's a mistake.
You're very efficient. The charge transfer is very efficient. Yeah.
Oh, sorry, thank you.
The question was about the charge transfer before you get to the readout state.
Yeah.
And the efficiency of that, which is very, very high.
You don't lose that electrons, really, right? What can happen is that if a pixel has like 1,000 electrons in it, and as you shift it, you can lose some of them, they leave some behind in the pixel. They don't all get shifted necessarily. So if there's a large event that we see a cosmic ray, we will mask the region above it and just not consider it. Sometimes that has single electron events in it, which is just from charge transfer efficiency. But we don't lose them as such, they're still there. Yeah.
Let's say I'm not worried about the galaxy blocking, but the top of the atmosphere does. So that energy deposition at the top of the atmosphere, that caused the atmosphere of the Earth to be lost on an 80-year time scale.
Good question, I haven't thought about that. Yeah, I don't know. Okay. I'm not going to waver a guess. Okay, so the region has a lot of problems. Anyway. If it is open, then we do it.
All right, interesting. So I will invite those without PhDs to come to the front and spend a few minutes with our speaker. And the rest of us can go enjoy a glass of wine and